Okay, so today we're talking about energy balance, and the problem that we're looking at specifically is water from a 3-meter tall by 30-meter diameter tank flows vertically down a 7-meter length of 1-meter diameter pipe. And that goes into a gold-plated jacuzzi through a 10-inch diameter horizontal nozzle. And then the water depth in the jacuzzi is kept at 1 meter by pumping the water back into the tank. So the question that we're looking for is how much power does the 100% efficient pump require? And then the second part is if the pump is perfectly insulated, which means no transfer of heat, is a chiller necessary to keep the water at the same temperature? So to start, I'm just going to draw out a diagram here just to be able to see it. So we're looking at a tank that flows vertically downward, and that's into the jacuzzi, and we have a water line there and there. And so now we're looking at out, we're going to call that 3, a point here 2. And then this is the power back in. Call that point 1, and we'll use a different color here to show the numbers that we were given to in the problem. So we know that this is 1 meter. This is 3. The length of the pipe here is 7. This is 30 meters. This is 1 meter, and then the nozzle here at the end is 10 inches, and then that's all that we need for our values. But we do have some reference numbers that are going to be used for future equations that we're going to use in this problem. So just to write these down here, we're looking at P1, Z1, V1, P2, Z2, and V2. So this is 0, so P1 is 0, so is Z1 and V1. And then P2 is 0, Z2 is -9, and then we're looking for the second velocity there. So using Bernoulli's equation, just to start, we're going to write down what that equation is. So Bernoulli's equation, and we have change of P over rho, so that's change of pressure over density plus gravitational constant times change in position, plus V2 squared minus V1 squared, so velocities over 2, and that's all equal to WNF non-flow work over M minus change of V minus Q over M. So that's Bernoulli's equation, and we're just going to eliminate terms from the reference numbers that we put up here to simplify this equation down. We're going to start with this left side. So we have delta P over rho plus G change of Z plus V2 squared minus V1 squared all over 2. So we know that P1 is 0, so all we need to do is cross that out because that makes that whole term 0. V1 is also 0, so you can cross that out there. And then the change of Z, we'll rewrite this as G times Z2 minus Z1, which is -9 meters minus 0 meters, plus V2 squared, because this 0 is going to cancel out that term there. This is just over 2. So now we have -9G plus V2 squared over 2 equal to 0. And then solving for V2, you get the square root of 18G. So I'm going to bring in a second piece of paper here to keep going with this. Move this one out of the way. So now what we're going to be looking at is the flow rate. So Q dot. So that's going to be the area times the velocity. And we know that in this case, since it's cylinder, pi r squared. So you're looking at, for the diameter is what we were given. So it's just going to be diameter over 2. So as it was given 10 inches, we're going to need to convert that to meters because everything else is in meters. So 12 inches to 1 foot, 3.28 feet to 1 meter. That's all over 2 because that was the diameter. So we need the radius squared times pi. And then for velocity, we just solved for that, 18 square root of 18g. So this is going to come back into play after our next equation. So what we're looking for is power, which is Q dot times the non-flow work over m. So that's WNF over m. So backing up to Bernoulli's equation, we know that change of P over G, or over rho, plus G times delta Z is equal to WNF over m. So we know from our original values that were given on the previous page, this is still 0, and then this is G 0 plus 9 equals WNF over m. So just to simplify this, you get 9G. So we can just substitute that back into here, which goes into this equation at the top. And we just solved for the Q dot above, so we can plug that back in, and we know that power is in watts, so that's all going to be equal to 10 inches times 1 foot. So these are just conversions. We're just copying this from above. That whole thing is squared. 18G, so this is your Q value. And then you're multiplying that by the WNF over m, which is just equal to 9G. So after plugging in the gravitational constant and solving for power, you get it's 59.4 watts. So basically what we're looking at is a comparison of WNF over m, which goes to potential energy, kinetic energy, velocity 2 squared over 2, and that's equal to CV change T. And then the second part of this problem is talking about a chiller. So is the chiller necessary? Yes, that's the answer to that one. So without it, the energy in the hot tub would just continue to build up, and it's a way to release that built up energy. So in this case, yes, we are going to use a chiller.